This is the first in a series of videos that's going to take a look at the code that I used to create the simulation in the rain problem video. The first video is going to take a look at how we create the raindrops and move them on the screen. The second video is going to take a look at how we move the boxes, the colliders representing people, and detect whether they've collided with raindrops. And then finally, the third video will take a look at how we make the graphs for that video. We start out here with just this empty list called raindrop list. This is just keeping track of all of the raindrop objects we've created. Every time we generate a new raindrop, we'll add to it. Every time a raindrop lands, we'll remove the raindrop from it. The ground here is just a visual so we can depict where the raindrops are falling. So we give it a position, we give it a size. Here we've got our space that we're working in. So these are just the bounds on where the raindrops are going to appear. At first, we're just going to work in 2 dimensions. So we're just going to ignore the Z direction. And then at the end of the video, I'll show you how we add in the 3rd dimension to give you a better idea of how the code works. Here we set our gravitational field, good old 9.8 newtons per kilogram. And here we currently have this drops per second. So this is going to be the number of drops we get for every unit of time in the code. When we expand this to 3D, we're going to turn this into drops per second per area so that we keep the raindrop generation consistent as we change the size of the area that we're working in. Let's skip these functions at first. Let's come to them when we get to them. The first thing we're going to do is we're going to make an initial set of 10 raindrops, just so that we have some initial raindrops to look at. They're going to be made using this code make raindrop, and for this we put in the bounds that we're working with, the xmin, xmax, ymin, ymax. So this is a square within which we want the raindrops to appear. So that calls up to this function here, make raindrop, and it accesses the raindrop list we've got here, and it creates 2 random coordinates. This function uniform is available in the random library, but I haven't yet figured out how to import that here in GlowScript, so I've made my own version of it here. Basically, the way it works is you give it a minimum value and a maximum value, and it picks a random number between the 2. So this built-in function random just selects a number between 0 and 1. So when you make this construction here, it's got a minimum value of x1 and a maximum value of x2, corresponding to random, giving you 0 and 1, respectively. So this is going to kick out something that's between x1 and x2. So for these 10 raindrops, we'll get 10 random pairings of x and y. So we'll have x anywhere between xmin and xmax. That's going to be between -5 and 5. Y we have set to be between 4 and 6. So it's starting somewhere up above, at some different altitude. And then we basically add to this list a raindrop. So a raindrop is going to be a sphere. It gets its initial position from those randomized coordinates. We color it blue for visual sake, and we give it a small radius. So these are going to be small things. Later, if I can remember, we're going to add on make trail to this because it's kind of fun to watch follow the trail of the raindrops. And then, of course, we also have to give these things a velocity. We're going to initialize their velocity to be 0. So we're assuming they're coming out of a cloud somewhere at 0 velocity and accelerating downward. Speaking of accelerating, it's time to move the raindrops. So here we keep track of our frames. So each frame is going to be a step forward of dt equal to 0.01. So we've got a pretty small time step. So from that, we can calculate the number of drops per frame. So we take the number of drops per second times the number of seconds per frame. So that's probably a good note to make here, as this is the seconds per frame. And so that gives you the number of drops per frame. So if I think about the numbers I'm using here, I've got 100 drops per second times 0.01 seconds per frame. When I calculate drops per frame, it should give me 1 drop per frame. So every increment of this code, it's going to give me 1 additional drop, as we'll see below. Here we've got our while loop. I've set it to repeat indefinitely, so it's never going to get to this print end of program. I just always like to have this just in case I need to check that the program is getting to the end. The rate is just the number of frames per second in real time that you see. And then we have this subroutine move raindrops. This is so that we hide some of the messier parts of the subroutine. We'll look at that in just a second, but what we see here is for each frame, we create more drops. So we're going to be creating 1 more drop per frame, again calling that same subroutine make raindrop So every frame we're going to get one more raindrop. So let's take a look at this move raindrops. Basically, this move raindrops routine is the Euler-Kromer method applied to the entire list of raindrops. So we access the list of raindrops, we access the strength of the gravitational field, and then we start to loop over the drops in the raindrop list. Here we just move the raindrops, so we update their velocity first, and then we update their position. It's important to do it in that order so that our code remains stable. And then we need to check for whether the raindrop has hit the ground yet. So the ground is located at 0, so we just do a check for this raindrop's position. And basically, if its position is less than or equal to 0, it's fallen to the ground, and so we need to remove it. And we need to actually remove the object itself from memory so that our code doesn't eat up more and more memory. So the first step we have to do is we have to make it invisible. VPython wants you to make objects invisible before you delete them. That's kind of a polite thing to do, I guess. And then here we simply delete that item. Now what's neat about it is when we delete this item, it removes the object from the system, but it also removes the entry in the list, and all the rest of the items in the list shift down. And so we only need to increment this counter I if we're not deleting a raindrop. It'll automatically go on to the next one in the list in this while loop. So when we run this, we should get one new raindrop each frame, and then see the rest accelerate down. Here we go, they're accelerating downward. We've got them popping in here in this window as promised. I can right click to rotate, and I can zoom out. And so this will just continue on and on as long as true is true, which is wonderful. I want to try a couple things just to illustrate for you what this is doing. Let's turn on the make trail for this thing. Make underscore trail equals true. This is going to leave a little path that each of the raindrops follows, which is kind of cool. I mean, you know, you get to see the ghosts of all these raindrops that fell in the sky. It's, of course, moving a lot more slowly because it's having to keep track of all of this information, but that's kind of a cool option to have. And then as promised, I want to add on the third, I want to add on the third dimension here. I keep hitting Control S, forgetting that this thing automatically saves. As promised, I want to add on the third dimension here. So let's make a new command here to create a random coordinate for zmin to zmax. And of course, that means we need to input zmin and zmax, zmax. I guess I could just access those as universal, or excuse me, as global variables, but it just seems to be, I don't know, it seems like there might be a case in which you want it to be raining more heavily in one area than another. I don't know. So here we're adding in the z position. We don't need to change anything about the velocity because it's only falling in the y direction. We'll try making it fall in an angle another time. And here I just need to change the call here to have zmin, zmax. And then same thing here. I should have copied and pasted earlier. Copy, paste, and that should give me an animation in 3 dimensions. Now this is also going to run more. Will it run more slowly? I don't think it will. No, it won't run more slowly. Yeah, because we haven't changed the number of raindrops. So now we've got raindrops falling all over the place here. Now I mentioned earlier we would want to change the significance of this raindrops per second to drops per second per area. That way we can scale the size of this thing without having to adjust the number of raindrops and keep the rainfall consistent. So what we're going to do is we're going to multiply this thing now by the area. So that's going to be how wide it is in the x direction times how long it is in the z direction, or how deep it is in the z direction, maybe I should say. So you got x max minus x min times z max minus z min. Cool. Now let's think about this. So that's going to increase this thing by a factor of, this is going to give a factor of 10, this is going to give a factor of 10, so that's a factor of 100. So in order to keep my my code from running too slowly, I should decrease this by a factor of 100. That should give me the same amount of rain. Drops per, oh, right. I need to actually change the name of the variable. Drops per second per area. Let's just copy this and paste it here. There we go. Okay. I was afraid I was doing something wrong with the integer argument for a second there. Okay, wonderful. And so now we've got this. And so now what I can do is I can change the size of this field and it will keep my rainfall consistent. So for example, I can make X-min go out to -10, so we'll double, no, we're not doubling, are we? So we're increasing the length of one side by 50%. Yeah. So okay. Oh, and I haven't changed the size of the ground, so I need to make the size of the ground proportional to that. But you can see I've got a bigger square here. It's bigger by half on each side because I've got the Z-min and Z-max connected to X-min and X-max. But the rainfall is consistent, so that rainfall rate is now an intrinsic property. So just to tidy things up, let's move this ground down here and have the length be X-min minus X-max, and oops, wrong way, X-max minus X-min, and the width be the same thing, or not the same thing, but the same thing for Z-max minus Z-min. And I guess what I need to do to get this thing positioned is I need to have the average of X-max and X-min times 0. Oops, not 8.5, 0.5. There we go. And this just gets it centered right where those things are. Z-max and Z-min. Run the program. Beautiful. And now no matter what I change X-max and X-min to, the rainfall will adjust and the ground will adjust. So if you like watching the rain, this gives you some virtual rain that you can watch to your heart's content. Next time we will take a look at how we make those red and green blocks that move across the parking lot and how we detect collisions with the raindrops. So thank you so much for watching. I will see you next time. Bye-bye.